I think it's already 10 past 2 o'clock. So welcome back, ladies and gentlemen, to our Precast webinar series. This is the seventh series of our webinar series, and we are coming to the very last session of our Precast webinar series. We'll be having Professor Antoni as the speaker. So Professor Antoni is a professor in the Civil Engineering Department, Petra Christian University, and he's currently the head of the Concrete Material Laboratory. He got his bachelor degree from Petra Christian University, his Master of Engineering degree from Asian Institute of Technology, Thailand, and his doctoral degree from Hokkaido University, Japan. His research interests include high-performance concrete, utilization of waste material in concrete, durability of concrete material, and repair and retrofit of concrete structures. So the title of his presentation will be Degradation of Concrete and Steel Building. So the time for presentation will be 45 minutes, and then will be followed by 30 minutes for questions and answer session. So time is yours, Professor Antoni.
Oh, okay. Thank you, Pak Jimmy. Thank you, everyone, for still staying with us until the end of the webinar. I hope you learn a lot, even though that perhaps sometimes the topic is relative new to you, but with the hearing from the expert, then you can understand what is the challenges and what is the advancement that they have already done and already faced. So our webinar is aimed to increase our knowledge in the application of precast, and then in Indonesia we still have a long way to go to catch up with the construction industry in other country, mainly in the precast field, because up to now we still have some precast building. We already have the precast building, but still the system is not as widely accepted because of many of our own concern rather than the precast technology. So our goal with this webinar is for you to understand, and then we can hear from the expert. So from my side, actually I study a lot about the concrete degradation. So the first speaker, Mr. Jyri, is mostly talk about the sustainability issue in the building, in the construction. So you know that the carbon emission is a very big concern with the global warming condition in the world. And then we have the changes of the climate and everything we must do to ensure that we also are ready for the future. I think the precast technology is one of the solutions, so we can make a good and durable building. But before we are making a good durable building, we still need to understand the mechanism of degradation in the building so that we can avoid it. So that is my presentation for today. So I still hope for the good discussion. And then my topic today is about the degradation of concrete and steel building. So I will start with the term of durability. So durability is the term that is being used widely, but actually it is a qualitative performance. Durability showing that it is long lasting. To put it simple, it's like to resist again the deteriorating action from the surrounding environment for the surface life of the building, of the material, or the system that we want to use. And then this is surface life. So surface life is the time that we want to use a building, and then actually we want to make the surface life as long as possible, but still reasonable economic. So normally we see the solid line here is that there is a performance that we want to obtain from the building, and then the minimum is like the minimum requirement for the building. And then when we use it, there is some degradation, and then when the degradation reach the minimum surface requirement, and then we call it the surface lifetime. But sometimes there is a premature degradation, so we can repair it. Or another time we have to improve or we increase the performance of the building, and then we call it retrofitting. So this is like the common performance of building during its lifetime. And then we see the building, mainly the precast and the concrete and the steel building is controlled mostly by the concrete. And then for the steel and connection, I think the precast connection also, we have the steel degradation. I will talk it on the second part. But for the first part, I will talk about the concrete because it's the main issue, the main performance. So the concrete durability actually influenced by two factors. One is from the internal, from the concrete itself, and the other is from the external. That is the exposure, so the aggressive agent, the climate, the loading, and others. This is a very complex interaction. While for the internal factors, is mainly by the compressive strength, because compressive strength showing to have a high performance in its durability. So we can have a good quality concrete with good strength, with high strength, and then we have a good durability. But also during the construction, we can also improve the durability by providing a good curing condition and also using some kind of admixture. So this is the basic of what I want to talk about. And then for the deteriorating action in the concrete structures, or in the concrete member, I see the concrete member I talk about can be applied to reinforced concrete, precast, or even pre-stressed concrete. So I think it's similar, but with the detail that is different, like the limiting factor. So for the deteriorating action in the concrete member, we have two types of deteriorating action. One is the corrosion of the reinforcement, and then this is the mostly we can see in the old building that there's some stain, corrosion stain is coming out of the building. Then we know that the building had been corroded, the reinforcement had been corroded. And then the second part that is not so much talk about is the corrosion of the concrete itself. Corrosion in the term of the degradation of the concrete materials. So we have example, chemical attack, frost damage, alkali, and then erosion. So this is the topic that I want to talk about, and mostly about the basic. So when we see or we can prepare our building to resist the said deteriorating action. And this is actually the performance requirement. So we can start from the bottom. So we have the safety requirement from for the building, and then the serviceability, and then the appearance. So appearance, safety, and serviceability is the performance that are required from the building, and then how it's behaved is actually start from the construction of our building. So when we are making a concrete building, like our design, our materials, the workmanship, and then the curing, and then the maintenance normally affect all of the process of deterioration. And as in the concrete, so mostly attribute to the pores in the concrete, and then the pore will influence the transport mechanism, and then the transport mechanism govern the concrete deterioration and reinforcement deterioration. So this is the basic of the durability of the concrete structures. When we see the transport mechanism, actually what we need to imagine is that the concrete is not a solid material. The concrete is like a porous material. So I always say that the concrete is like a sponge, but very, very hard sponge with many pores, connected pores. And then all that kind of the pore can be infiltrated by the material from outside that can cause corrosion or chemical action or physical degradation. So that is the basic of the deterioration of the concrete structures. Now, for the transport mechanism of concrete, so when I say concrete, you can imagine like a hard sponge with many pores. The deterioration normally influenced by the transport within the pores and crack and the water in the concrete. So yeah, just for the information, the porosity in the concrete normally is open for the high percentage of water to cement ratio. And then normally the pores are interconnected, so it's connected. And then 20 to 30% in cement paste, that is the pore in the concrete. And then also one important thing to notice is the size distribution of the pore. Because when we have a very good concrete, the pore is so fine that the material from outside cannot enter. But normal strength concrete is have a larger pore distribution, and then the material from outside can enter easily. And then this is just the basic for the transport mechanism. We can calculate the degradation process, and there's a underlying equation that is the diffusion process, but I will not go into detail about the diffusion process. But diffusion meaning that there is a difference in the concentration. So the outside concentration is higher than the inside concentration. Therefore, the material will move. So the outside concentration could be acid concentration or salt concentration, and then it will move inside the concrete and then cause degradation in the concrete. Okay. And then the material that is moving are as follows. Sometimes we have a carbon dioxide. It will react with the concrete, and then oxygen also. And oxygen is needed to make the steel corrosion occurs. So oxygen, steel and oxygen and water is the main governing process of the corrosion. And the water always appear because inside the concrete we also have water. Outside the concrete there's a water vapor. So this is the transport mechanism of in the concrete. This is just information. So when the material can be controlled by changing the diffusion rate. The diffusion rate can be changed by making the concrete quality better. So this is just a basic for knowledge. And this is just a theoretical analysis. So I just showing that the diffusion process, there is two conditions. One is the stationary state, and the other is the non-stationary state. We will use each one depending on the problem that we will face. But yeah, this still some background of the deterioration action. So another thing is that the concrete is also like a sponge, so it will soak up material from outside, and it's controlled by the capillary suction. So the capillary suction is showing that when you have a dry internal part of the concrete, and then there's some water, the water will be sucked by the pore in the concrete. So this is also one transport in the concrete. So yeah, and then this is like the example for the process of drying and wetting. So we have time, and then when the concrete gets some water from outside, maybe from rain or from the seawater, the wetting cycle is very fast. And then when it's dry, the water will be released slowly. This is an example of that. So yeah, I want to say that the transport in the concrete, the transport of material in the concrete is a complex process. And then there is a capillary suction, there's a hydraulic pressure when there's water outside of the concrete. And then there's a evaporation, so there's a water transport in the concrete. And then that is the process occurring in our concrete. So there's a pore, there's a diffusion, there is some capillary suction, and then there's some moving of water. That is our concept from our building. Even though there is no deterioration, this kind of transport is still occurring in our concrete structures, regardless whether it's a precast or cast in situ concrete. So that's I want to talk about. That is the basic for the movement of the material in the concrete. So the next part I want to talk about is the deterioration of rebar in the concrete. So when you are faced with the durability issue in the concrete, this is actually the main factor. The rebar in the concrete is it's said to be able to be durable in the concrete, but up to some time. So this is the deterioration mechanism. So when there is for the new concrete with reinforcement, normally the reinforcement is being protected by the concrete. So the passive film, I see passive film is like some layer in the reinforcement surface. And then due to the high alkalinity of the concrete, we have the passive film. So the passive film normally protecting the corrosion. The passive film normally protecting the reinforcement from corrosion. But sometimes when the pH is reduced, the pH of the concrete is reduced by the action of carbonation and leaching out of alkalis. and also some chloride contamination, it also can destroy the passive film. So with the availability of water and oxygen, the corrosion of the reinforcement will start. And then the corrosion of reinforcement start, we have two types of degradation. One is the reduction of the cross-section of reinforcement, and the other is the cracking and spalling of the concrete. So overall, it will cause the degradation of structural performance of the structures. So this is the mechanism of the normal reinforced concrete building. We have carbonation, chloride, and leaching out of alkali. So I will explain about the carbonation. So what is carbonation? So when you have a concrete, normally the cement react with water, producing a CSH gel, calcium hydrate gel, and then the calcium hydroxide solution. And then the calcium hydroxide is very high in alkalinity, so it will protect the reinforcement. And when the carbon dioxide penetrate into the concrete, it will react with the calcium hydroxide, and then producing calcium carbonate and then water. With the reduction of the calcium hydroxide content, the pH in the concrete will reduce. And when the pH is less than 11, the corrosion will start on reinforcement. So this is the basic of carbonation. So we can calculate the carbonation depth in the concrete with time normally, depending on the quality of the concrete materials. Normally, the equation will follow this type. Y is meaning the concrete cover, K constanta times square root of time. So we have two conditions. One is indoor condition and outdoor condition, because when the indoor, we have a higher concentration of carbon dioxide. So this is the indoor condition. So the carbonation can enter more rapidly into the concrete. So when the pH is less than 11, we can say that the concrete will lose its, the reinforcement will lose its protection and then start to corrode. So this is the basic of carbonation. And then the distance from the concrete surface, normally we call it the concrete cover. So when the pH is reduced, meaning the left part, when we have rebar on the left part, it will lose the protection of passive film and can start to corrode. So this is the process of carbonation. Now, we can detect the carbonation of concrete using phenolphthalein solution. So when we use phenolphthalein solution, we spray it on the concrete. When the concrete change color to the pink color, showing that there is some calcium hydroxide in the concrete, and then this part is still relatively high pH, while the outside is already lower pH. So this is the carbonation. So when the reinforcement is on the pink side, 1 centimeter from the pink side, showing that the concrete is still not yet carbonated, and the reinforcement can still be protected with. When the reinforcement is on the non-changed color side, so we can say that the reinforcement is not protected by the concrete, and corrosion can start to happen. Now, another degradation is the chloride penetration into the concrete. And the chloride source normally is from the seawater or de-icing salt. So chloride is actually a very deteriorating agent in the steel. So we have steel structures also, and we also have the reinforced concrete. When exposed to seawater, the degradation normally is very fast due to the chloride effect in the process. So yeah, this is some information that the chloride diffuse into the concrete, and then when the critical concentration accumulate in the reinforcement, the corrosion will start. So differ from the carbonation, the chloride penetration penetrate faster, but chloride only we can find chloride in the marine environment only, and maybe in some the country using the de-icing agent. So the chloride concentrate, the penetration rate of chloride using the fixed second law. This is some theoretical background, but yeah, just for information. And then one thing that we need to understand is that the chloride will cause degradation in the reinforcing bar when it's reach its critical chloride content. And then there's some standard. This is the Japanese standard saying that 0.4% of chloride related to the cement weight can cause corrosion in the reinforcement. And this normally translates to maybe 20, 30, 40 years of exposure time. And for the pre-stressing in the concrete, pre-stressing still in the concrete, it is lower, even lower the concentration to cause the corrosion. So this is some information. When the corrosion of the reinforcement occurs, so in this case, the chloride enter into the rebar. So this is the corrosion condition. We have anodic condition and cathodic condition. There's a movement of electron, and then the rebar will start to corrode. So this is the basic of the degradation of the reinforcement in the concrete. And when the corrosion is occurring, we have a steel alpha Fa, and then it will expand. So the expansion is due to the change of phase in the material. So normally it will change into the ferric oxide, and then the rust that you are seeing normally, you can see in the with the red color is normally the Fe2O3 3 water element, and then it have a 6 times of the volume. So the 1 millimeter, maybe 1 millimeter of the steel reinforcement that being corroded can change to 6 millimeters. So it's expanded so much. So this is actually the cause of why the concrete spoil, why the concrete is cracked, because due to the expansion of the rust. When the corrosion started, the rust will expand, and then our concrete will have the tensile stress. And then when the tensile stress is higher than the tensile strength of the concrete, it will crack. And the cracking is, we have two conditions. One is the thin cover, it will spoil, and then thick cover is just crack, and then the rust will come out from that part of the concrete. So we see the basic of deterioration is like this. And then, yeah, this is the degradation process. So normally we divide the degradation process of the building in 4 stages. One stage is nothing, because we don't see what happened in the concrete. Normally is the salt water enter to the concrete building, or the carbonation front is moving. So stage 1, no degradation. Stage 2, when there is a static condition, crack appearing. So when corrosion and then crack, so we call it stage 2. And then for the waterproofness is the crack will cause some problem. And this is the waterproof has decreased. And then for the load bearing capacity, the red one will reduce stage 3 and stage 4. And safety also reduced so much. So when the building is going to the stage 3, the degradation is accelerated. And then sometimes it costs more to be repaired, because we can see the degradation already. And when you can see the degradation, not meaning normally is much more than that. Okay. That is the normal degradation in the concrete building due to the steel corrosion, steel bar corrosion. And then this, the second part is the deterioration of concrete. So actually concrete is quite straightforward. We have the attack from the environment and also the problem in the concrete itself. When the concrete have some reactive substance in the beginning, the degradation will occur. I will show you later. And then from environmental, normally is due to the aggressive substance, and it will transport into the concrete and cause some chemical reaction. So this is the cause of the deterioration of concrete. And normally we don't have much already, because the chemical attack on concrete, we understand so much, and then we try to use material that is good quality, and we can also limit the aggressive substance coming to our building. So, but this is just the knowledge that you need in order to prepare your building. When the chemical attacks happen on the concrete, normally it can be divided into the following condition: the acid attack, because acid is also a good agent to destroy your building. And then the reactive substance is hardened concrete, meaning that all the concrete part will be destroyed by acid. And then another thing is the sulphate attack. Sulphate is material from the seawater, and also some soil also have sulphate. So sulphate is material that attack the aluminate component in the Portland cement. So aluminate react with sulphate. And then the other thing is alkali of the concrete react with the aggregate. So for the acid, we have lots of acid that we need to understand. There's some hydrochloric acid, sulfuric acid, nitric acid, and organic acid. Normally, the building will face the organic acid because we have oil spill, and then other type of acid. Cleaning solution acid is also this part, and then it will convert the calcium compound of the cement, reacted cement, into the calcium salt. So this is the schematic. Acid exposed to our building, and then it will convert all the layer of this hydrated cement. This is the acid attack. And sulphate attack is only reacted with the limited content component in cement. And after that, it will expand and then cause disintegration. So this is the sulphate attack. Mainly sulphate will, from the environment, will enter the concrete and then reacted with the pre-calcium aluminate component, the black one. And then after that, it will expand and then cause some crack in the concrete. So yeah, sulphate attack. Mainly, we can reduce the sulphate attack by using low aluminate cement. So this is actually the basis for the cement in the marine environmental. Yeah. So yeah, limiting factor is the water to cement ratio. We reduce it to 0.5. So this is the Japanese standard. So this is the sulphate attack. And then, yeah, cement type. Sulphate attack is the degradation factor in the concrete. Because for acid, we try to protect it. But for sulphate, we still have a building that is exposed to sulphate. And then for the alkali, actually, we have alkali silica. Silica is meaning the aggregate contain silica, and carbonate, our aggregate containing the carbonate, like limestone is also carbonate. With the reactive aggregate, high alkali concentration and moisture, it will expand and then causing some cracking, map cracking in the concrete. So yeah, the process is like this. When alkali or from the concrete inside react with the aggregate will expand and causing some crack. So the alkali silica reaction is a very old condition because we have many concrete structures and then they have a cracking. This kind of crack, map crack, is the alkali silica reaction. So this is also the same one. There's some leaching of alkali in the cracking. So that is the deterioration of the concrete. Now, for the steel structure is quite common, but actually from the steel structure, we can see the connection with the precast is like the connection, the joint of the precast member. Mainly we use steel, so also related to the steel. So for the steel superstructures, there is many typical damage. So deformation, distortion, collision, connection damage, and tightness. This is related with the design, the steel design, and then the construction, and then the maintenance process of the steel structures. So this is mainly mechanical damage. And then for other part is the coating, when we coat the concrete with some paint. Another steel, we also use the corrosion protection using galvanizing. So galvanize is also some kind of corrosion protection. And then for the when we use the building, we have the fatigue condition. Fatigue is like the cyclic loading in the concrete, and we also have a fracture condition with overloading and cracking. Yeah, cracking is similar to the fractures. And fire is damage that, yeah, some kind of building. But the main problem of the steel superstructures is the steel corrosion. This is what we need to understand. When we understand the corrosion process of the steel, hopefully we can avoid it. So there is 5 types of corrosion. One is uniform, and then galvanic corrosion, crevice, pitting, stress. I think the one that is related to the precast structures is the galvanic corrosion so much, and then crevice. Crevice is the corrosion occurring on the unprotected part of the steel. I will explain it later. So for the coating, this is also related to the precast, I think. And normally for the steel building, we see that the coating, we have a local failure of finishing. So meaning that scratches or some impact will make the finishing fail. And then normal weathering is good because then we can just reapply the finishing, and then some failure of the painting system. And there's some tests also to check. It's a holiday test. Normally we use some sensor and we check if there's some exposed surface. And then, okay, for the steel corrosion, this is the uniform corrosion. This is normally what we see in the steel building is the uniform corrosion, that is a uniform thinning of metal without any localized attack. So this is, we can see there's some part is localized. Actually, it's considered as pitting, but when the overall part is corroded, we can still consider it as the uniform corrosion. And this is normal and still okay when we have very thin. And normally for the uniform corrosion, we can protect it using the coatings, plating, galvanizing, or anodizing, or using corrosion inhibitors, or even using the anodic protection. Or even we just increase the thickness of our structural member. And then the pitting corrosion, this is when the localized corrosion occurs and cause some damage deeply inside the steel and cause holes. So there's many type of corrosion, and normally due to the process of making of the steel, I think the process is not quite uniform, and then you have some local condition. So the material need to be selected very well. And then there's some salt attack also. So when in the marine environmental, we have chloride attaching to the steel, this is also causing the pitting corrosion. Yeah. And for the stress corrosion, this is we hardly see, but this is just one knowledge that we need to know, that stress is normally occurs on the tensile phase of the steel, and then when the tensile stress is occurring, the aggressive substance can enter to the steel and causing some corrosion. So it's also occurring when the high temperature. So for boiler, normally stress corrosion also occur. And for the one that we need to pay attention for the precast connection, I think, is the crevice corrosion. The crevice corrosion is the condition of corrosion when there's some shield, some plate outside of the steel. So this is the crevice corrosion, because when we have a condition that is protected from the outside, the water here cannot be dried out, and then with some salt, it will cause very high acidic condition and then pitting condition here. So this is when we have a two part of the concrete or the steel plate, and then there's some gap there, water can enter, and then corrosion can occur. So this is the most important corrosion process, I think, in our steel and concrete connection. That's why we need to have a very good filling material, grouting, so we can avoid the occurrence of the pooling of water in this part. So we need to fully drain, and then yeah, can reduce it. Yeah, that is graphis, I think. And also one important condition that I think for the precast connection is the galvanic corrosion. So galvanic corrosion is actually a very well-known condition. That is when the two types of metals are connected, there's a reaction. That is why we have a galvalume, right? The lightweight steel, because we have aluminum and steel. The aluminum will protect the steel. So this is an example of two dissimilar materials. We can see here that the bolt and the steel plate have a different metal type. And then the left figure showing that the bolt and the plate, the plate have corrosion because the bolt maybe have a higher galvanic potential. When the third one is the bolt is being corroded. So this is also not good condition because this is the bolt is being reduced the strength. So, but this is can happen when we are using different type of metal as our connection. So I think for the precast member, the galvanic corrosion need to be considered very well, because different type of metal will have different potential corrosion potential. Of course, this condition occurs when there is water and oxygen. So one thing that we are trying to do is also ensure that our connection don't have water and oxygen by filling the connection with the grouting. So that is called the rigid connection. Now, this is one information for the galvanic series. So our mild steel is here, mild steel, and then low alloy steel. Stainless steel is higher. So when we are connecting the steel, stainless steel and mild steel, the one that is going to be corroded is the mild steel. As long as the volume is very high, so it's no problem. But when the lower part is have a less volume, so it could have a problem. So like when we have a zinc is quite low, and then magnesium is very low. So when we connected the mild steel and aluminum, the aluminum will corrode. This is also the condition when we have aluminum roofing. We have aluminum roof, and then we connect it to the steel. The aluminum roof cannot last long because the galvanic corrosion. The same happen when we have stainless steel plate connected with the low mild steel bolt. The mild steel will be corroded. So this is the condition. And one thing that is interesting to see is the graphite. Graphite is very high, and you can see the graphite is like the pencil, the content in the pencil. So this is a very corroding material. That's why when we are scribing line in the steel, the graphite left there will act as the corrosion. So normally when we are making the marking in the steel, we try to avoid using pencil. Just use pen. Yeah, for galvanic corrosion, we can prevent it by using a material that is similar corrosion potential, or breaking the electrical connection. So we have to separate using some plastic. We can use it, and coating, yeah, spacer, and then that's the same. Or we can use sacrificial anode, or using corrosion inhibitors. So yeah, the galvanic corrosion, I think, is a main knowledge that we need to have for the precast concrete connection. Also, this is the last slide, one slide before the last. The most of the problem of the degradation in the building is due to the water. So water infiltration is the main cause for the concrete, steel, or even other type of building, because there is water will cause some corrosion or other degradation in the material. So why water can infiltrate normally due to the joint connection, water puddle. So that is also one problem that happening in the building. We need to have a good maintenance, leaking, and then other water source. So I think that is my presentation. And for recaps, the durability factor we need to consider beside the strength and workability of when we are making a good building. And then internal and external factors need to be considered. And then, yeah, the mechanism of degradation we need to understand so we can make a good concrete. I think that is my presentation.
Yeah. Thank you, Professor Antoni, for your presentation. Now we are entering the questions and answer session. So for those of you who want to ask your questions directly to Professor Antoni, you can raise your hand, and when I call your name, you can unmute yourself and ask your questions. Okay, is there any questions? So for those of you who also want to ask in Bahasa, you can also write down your questions in the chat room. I think Professor Antoni can understand Bahasa. So there is one question from Mr. Arif Wibowo. This is a very long question, so I will try to read it. The durability of concrete we made will increasingly be much more challenged by Mother Nature as a result of the climate change. It is an irony since the way we produce cement also release massive carbon to our atmosphere that accelerates the climate change. How do we do our constructions without exploiting our natural unrenewable resources, especially for concrete structures? Will it be implemented internationally to slow down significantly the climate change, since Indonesia has abundant and affordable natural resources which soon or later will certainly be depleted and causing unthinkable disaster to the environment of Indonesia and the whole world? Maybe you can answer the question, Professor Antoni.
Yes, I think the durability issue and the sustainability issue is everything every country need to face. Like one thing that is been bothering me is like the cause of global climate change, or the greenhouse effect, is mainly due to the release of carbon in the atmosphere. And the release of carbon is mainly due to the burning of fossil fuel. So when we are burning fossil fuel, we are releasing the carbon into the atmosphere, and we are causing global warming. And when we are making cement, we also use that kind of heat to heat our cement, and then we can make it. But when the cement react with water, actually it absorbs some of the carbon dioxide, but small part. So the cement is not as much problem as the other fuel burning process. So that is one thing we need to understand. But to make durable structures, yeah, we have the knowledge to increase the concrete strength by reducing the cement content. so we can have a more durable. I think that is one way to go. And then we can also optimize our structures using a smaller member size. That is also one way to go. And then the precast is also one solution, because we reducing the construction process. I mean the waste, and that is I think one way to go. But from what how do we do construction without exploiting our natural unrenewable sources? I don't think there is a way to do it, because still we need to use unrenewable resources. But we can optimize it. We can make the structures to be long-lasting. With long-lasting, of course, the costs will be reduced, and also we don't need to spend more energy to rebuilding it. So I think, yeah, our way of doing it is all front. We must do it. Yeah, I think that I can say.
Okay, so I think that should answer the question. So about the unrenewable resources, so if you want to build the structures with renewable resources, you can build with using the wood. So when you plant the, I mean, when you cut the one tree down, you plant one tree, so that of course it will take some time to the tree to grow up again, but it's still renewable resources. So that's why, I mean, in the first session, I think Mr. Jyri said that there is now is a trend that people are moving towards wooden structures to create more sustainable structures.
Yes.
But again, it will have another problems also. Okay.
Yeah, the time also.
For the second question is from Mr. Henry. Our question is there any way to increase the performance of the surface pores of the concrete to avoid deterioration of the reinforcement inside?
Yes, that is a good question. Like the deterioration of the reinforcement can be reduced by increasing the concrete cover. That is one thing we can do it, but of course the member will be bigger due to the increase of the concrete cover. And then another thing is we can use higher compressive strength concrete or higher quality concrete, so the pore will be smaller. We can make it using low water to cement ratio. I think the simplest way is like just to increase the compressive strength of the concrete, but with reduced cement content, and then we now have many admixtures product we can use in the concrete. That is one way to do it. Another way, there is some technology. We can use the coating. We can use coating. There's many types of coating, and we can use the permeable membrane as the. I think that's many technology to do. But the basic thing I want to say is that we can increase the concrete quality, but still try to reduce the cement content. Yeah.
Okay, thank you, Professor Antoni, for the answer. So we are moving to the third question from Mr. Andreas. The question is, considering that carbon steel is vulnerable to corrosion, stainless steel has been widely used in the curtain walls. In addition, AISC also has some design guide for structural stainless steel. Could you share your opinion regarding the usage and development of stainless steel for structural steel or even for reinforcing bars? And the second question is, how do we monitor and judge whether the corroded bars or steel members are acceptable or severe that some retrofit actions are needed?
Okay. Yes, for the first question, stainless steel for structural steel, even for reinforcing bar, I think is very good potential to be used as the rebar, because when we have the steel, it have a very high corrosion resistant, of course with the extra cost. And then normally we just use it for the structures that need to perform well even for a very long time. And then for the galvanic corrosion, I don't think there's a problem with steel, because when we have steel in the concrete, the same behavior will occur. And why the reinforced concrete have problem is due to the corrosion of the reinforcement. When the reinforcement will not corrode, so I don't think we have any problem, because the problem of corrosion in the reinforced concrete is due to the cracking of the concrete due to the corrosion expansion. When we don't have that kind of process, there's no corrosion in the stainless steel. So I think we will have a very good long-lasting building, but of course the cost will be very expensive. And previously there is one technology called epoxy coated rebar being used, because epoxy coating on the reinforcement can protect the reinforcement from corrosion. But after 20-30 years of evaluation, the problem is with the epoxy coated rebar is the construction process will cause some part of the coating to be damaged, and then the protection is gone. So we have problem also. But for stainless, I think it could behave very well. But one thing that we need to understand is that how is the connection from stainless steel with other part of material? So when you have stainless steel as the main rebar, and then you have mild steel as the bolt, all the problem will say that, all the knowledge will say that the bolt will have some corrosion, because the inside stainless steel is so much. So the anodic and cathodic area is the cathodic is larger, so we'll have a corrosion. But when we using stainless steel, and then the connection is also stainless steel, then there should be no problem. I think that is the question for the first question. How do we monitor and adjust the corroded rebar steel structures? I think that we need to see the standard also. Normally, yeah, this is a still engineering judgment. We need to see what is the extent of condition. So when there's a crack and spalling, I think that is the indication of the severity of the problem. But when there's no cracking, we still can measure the corrosion with some potential measurement, and then we can estimate the risk of corrosion. But yeah, we still need the second question, I think, is a topic that is need to be discussed further. That's my answer.
Okay, thank you, Professor Antoni, for the answer. So to in addition, I want to add for the stainless steel, I think we need to also to look after for the development length of the rebars, because the stainless steel has a less bond as compared to the normal reinforcement. So the bond between the reinforcement and the concrete is not as good as the normal reinforcement. So the stainless steel or the epoxy coated reinforcement will need a longer development length into the concrete, so that it can develop the full yield strength or the tensile strength.
Okay.
I think that is one consideration that we need to pay attention when we are using the stainless steel or the epoxy coated reinforcement. And then for the second question, I think, yeah, I agree with the Professor Antoni that it's very difficult to say that, okay, let's say we have corroded rebars, and if somebody asks how many percent that the strength left, it's very difficult to answer it because it's a combination of many factors, and we need to do a lot of assessment before we can come up with the solutions that are needed for the retrofits.
Yeah.
Okay, is there any other question? Maybe from the audience or from the students?
Yeah, for the building, I think most of the problem is due to the water infiltration. Yeah. So when we can avoid this kind of problem, I think we will have a good durable structures, but sometimes we still have to face it. Yeah, Pak Jimmy, ada pertanyaan lagi?
Are there any more questions for the Professor Antoni? Yes, Mr. Henry.
From your experience, Pak Antoni, you know that some cities are built upon water, like Jakarta. So, how would you advise regarding this kind of situation? Because just now you told us that water infiltration is most of the problems. Are we going to move away from water? It's impossible because human culture is built near the water.
Yes, I mean, when we are designing against the water, so it should be no problem. So when we are designing the structure to be in the sea, even we can increase the concrete cover. We can provide additional protection. So I think what I want to say here is when we are not designing it, the problem is mainly this. But when we are designing it, we can increase the concrete cover thickness. We can prepare coatings. So like the first presenter, Mr. Jyri, say that there's 3 types of coating with bituminous material, and then I think it's still good. But when the coating is failed, I think that is the start of the problem, or even when the maintenance is lacking. So we have a concrete roof, and then the water can puddle there. So that we need to give some gradation so it always dry. So what I want to say is about that one. Not when we are designing up against the structures in the marine environment, we can also provide a good protection. Yeah.
Yeah, thank you, Professor Antoni, for the answer. So there are many ways to protect the concrete structures when we build structures near the sea. And in addition, what Professor Antoni has mentioned, maybe I want to add one more method is we can also use pre-stressing for the structure. So we make sure that the concrete is all in compression. So we don't have any tension in any of the sections, so that we avoid any cracks that can cause the seawater to penetrate inside the concrete. That will help also for the durability of the structures.
Okay.
So the next question is from Mr. Hassan. The question is, which one is better in marine environmental, non-fly ash concrete or ordinary fly ash concrete with the same specified concrete strength?
Okay. This is, I mean, quite difficult question because it depends. In the marine environment, the problem is with the 3-calcium aluminate hydrated. So the 3-calcium aluminate content in the concrete is causing what happened. What is the sulfate attack? Normally, the marine environmental, we have the sulfate attack, and then the sulfate will attack the 3-calcium aluminate. So concrete with fly ash or concrete without fly ash, I think there's a similar tricalcium aluminate there. So the response will be the same, maybe the same. But then again, when you are replacing some part of the cement with the fly ash, meaning that the content of cement is lower, and then yeah, it could be beneficial to use fly ash in the marine environment, because like the content of tricalcium aluminate will be relatively lower. That is the question, the answer. But yeah, I mean, with the same strength, and then fly ash without fly ash, I don't think it will be matter too much. But I think that is mostly due to the tricalcium aluminate content. And with fly ash and non-fly ash, I think that is another field of discussion, because fly ash, there is a good quality fly ash, bad quality fly ash, and then the fly ash quality consistency, that is another way of thinking also. So the short answer may be the same, because it's depending on the tricalcium aluminate. That's why for some standard of the marine environmental structures, we always try to use the OPC type 2, so reduce tricalcium aluminate. I think that is the short answer.
Okay, thank you, Professor Antoni, for the answer. In relation with the question from Ms. Rasan, I also want to ask, is there any beneficial effect when we add the silica fume to the concrete for the marine environment?
Could be, because when we are using silica fume, we try to make the concrete denser. But silica fume is very expensive, and I don't think it's beneficial to use silica fume for concrete with the lower compressive strength than 80 megapascal, 80. So the use of silica fume can be beneficial, but that is too much cost, I think. It's better to use additive to reduce the water cement ratio to be lower. So this is one answer, limiting the water to cement ratio lower than 0.5. Yeah, for the GSE standard is 0.5. But for now, we can make 0.4 water to cement ratio. I think is already very good. So with fly ash or without fly ash, when we reduce the water to cement ratio, we provide a better protection.
Okay, thank you, Professor Antoni, for the answer. Is there any more question from the audience? Maybe those of you want to ask question directly or who wants to discuss some topics with Professor Antoni. Maybe some student who want to ask about the durability of concrete.
Yeah.
Yes, is there?
Okay.
It's already late afternoon. This is a weekend, so okay. If there is no more question, thank you, Professor Antoni, for sharing your knowledge and experience with us. I think it should be beneficial for all of us. So I also would like to thank all the participants who has been joining this webinar series from the first sessions until this last session. This is the 7th series. So we are coming up, has come to the end of the webinar series. So I would like to say thank you for your participation, and I also want to apologize if there is any mistakes during the Precast webinar series.
We have a closing remark also.
Thank
Pak
you again. Yeah.
We have a closing remark from our
Department
head, Pak Daniel.
I return back to Professor Antoni. Okay.
Yes. So yeah, we have a closing remark from our civil engineering department head, Pak Dr. Daniel Chandra. So, and then yeah, I thank you also for everyone to join our webinar for the final webinar. Silakan Pak Daniel kalau closing speech-nya. Sudah sudah.
Okay. Good afternoon. On behalf of Civil Engineering Department, I would like to say thank you to all participants and speakers also on serial webinar Precast members usage for structural building element. This webinar series have been conducted in 7 sessions. With first opening webinar session have conducted jointly with FIB and Rieckermann and Elematic on 28 August. After that, 6 webinar conducted with Civil Engineering Department, Petra Christian University, and Rieckermann and Elematic. The first webinar went well with more than 300 participants, and also 6 webinar series will have also run smoothly with around 100 and 150 participants from student, Indonesian construction practitioner, as well as neighboring countries, Malaysia, Singapore, Vietnam, and surrounding areas. I hope this webinar also increase the role of academic and practitioner to share knowledge with each other, so can accelerate the adoption of technology that is commonly used in developed country to be used in Indonesia as developing country. As I thank you also to organizing committee who have worked to prepare this webinar series. Thank you to FIP and Rieckermann Elematic. Hopefully this collaboration will continue in the future. On behalf of organizing committee, I wish you all have a blessed and productive time in this webinar. God bless you all. Thank you.
Thank you, Pak Daniel, for the kind word. So with that, ended our webinar session. So please, you can fill out the evaluation questionnaire, and then we will upload the presentation slide in our link, and then we will share you the certificate for joining our webinar by email later on. And on behalf of the organizing committee, I thank everyone in joining our webinar. And also I want to say we are sorry if there's some problem along the way. So I hope you can still have a good time with a good learning experience. And please give us good feedback for our future webinar also. Thank you, everyone. Terima kasih semuanya. Cukup? Terima kasih, Pak. Nanti akan di-share lagi.
Jangan lupa Pak, YouTube linknya Pak.
Oh ya, YouTube linknya ada yang bisa share. Kita punya YouTube link. We already have the YouTube link, and let me look for it.
Because we have some unattending participant who normally join every of the webinar, and they already said to us, please, since we could not attend this webinar, please share the material and also the YouTube link.
Yes, the YouTube link is in the. I copy into the chat room, so
Okay.
I will share. And maybe later on we will also share to everyone the channel. We have the YouTube channel. You can browse there.
Yes.
So we will also share the link to the YouTube channel, the link to the presentation material, and then the certificate.
Thank you, Pak.
Terima kasih semuanya. Selamat siang, selamat berlibur.
Terima kasih Pak.
Selamat berakhir pekan maksudnya.
Terima kasih Pak.
Have a good weekend,
Terima kasih Pak
everyone.
Hendri.
Terima kasih Pak Antoni. Terima kasih Pak Denny.
Pak Hendy, Pak
Denny,
Jimmy,
terima
Pak
kasih.
Daniel.
Semua Pak Antoni, Pak Jimmy, Pak Daniel.
We have also our colleague from Vietnam, Mr. Phan Chong Thi, and also I think Mr. Wu. He is also from Hanoi or Ho Chi Minh, sorry, Ho Chi Minh Technical University. Also attend this meeting. This webinar. So once again, thank you.
Ya, terima kasih semuanya. Thank you everyone.